Hello, good morning. In this session, we'll talk about image segmentation with PyTorch. We'll use, human database where we'll segment human images, as you can see here. But these methods can be applied for any image segmentation. In this, we have two different sections. One is environment setup, and second is the core network development and testing. We'll quickly go through the environment setup. We need to set up a Colab GPU environment. I'll just show you how it's done. You go to runtime, then change the runtime type here, and you just select a GPU here, and then save it. Then we'll install the required packages. Then we'll clone my GitHub directory to get the zip file and unzip it here locally for all the datasets. We'll append system path to include temporary folders created here. We'll develop helper methods to show images. In the core network development and testing, and that's where it's very interesting is, set a network configuration parameters. Then we'll read a CSV file which is part of the dataset, which contains images and associated ground truths path for them. Then we'll split our dataset into test set and validation set. Then we'll define the data augmentation functions. Then we'll create a custom dataset with the data augmentation. We'll load these datasets into batches with PyTorch data loader. Then we'll create a segmentation model. Then we'll create training and validation functions. We'll train and save the model, and finally we'll draw inference. So let's get into it. First is the environment setup. I already saw you how to do a GPU setup. Then in this, we'll install segmentation models, PyTorch. We'll use one of these unet based models. We'll use this augmentation library for the data augmentation. And we'll also use OpenCV, especially to read and write files and image files. And that's where we have used this in this project. So once we're done with the installation, we also need to download and unzip the dataset. I like to give credit to the original author, and the original dataset is available here. In this cell, we're just downloading the dataset. So you basically clone my GitHub directory. Then you unzip it. You just unzip here. I'm using the silent mode of unzipping to avoid too much of content here. Once we have unzipped, it will create a folder called HumanSegNet dataset in your current directory, which is content. We'll just append this in the system path, so it's very easy for us to refer those directories and the files. We'll import, as usual, the torch library. We'll import CV2 to read the files. We'll import NumPy. We'll use pandas, as we'll use it to read the file paths. We use plotting library, that's matplotlib. We'll use the sklearn model selection, and that's only one function we're using, that is to split our test and validation sets. And then we'll use tqdm just to display progress in our training process. Let's have a quick look at the helper function. This is show image. Basically, you can see there are three parameters: images, mask, and predicted mask. As you can see, predicted mask is optional because many times just to view our dataset we may not use it. We'll just use to view our image and associated mask. When we supply this predicted image, all three will be displayed. I'll not go into detail. I assume you know matplotlib. Basically, this is just to set up the parameters. And here, as you saw, we just show the images. That's all we have done. So with this in place, if you have any question, you can always ask me. But it's very simple. You basically create a 3 subplots. If there is no predicted image, and you set the title for image, you set another title for ground truth. You'll basically permute here and show a gray image. Okay, that's all we do. Let's move to the core network. First, we need to define the configuration parameters. This is the path for the CSV file. You will be able to see it here. It's right here. And this have a path for the training and associated ground truth. This is our data directory. Normally it's content in the Colab. We also set if CUDA is available, we set CUDA as our device. And that is a GPU. We set epochs. We can use 30, 40. Don't go beyond that, otherwise it will take a lot of time in training. LR is learning rate. We'll fix the image size to 320 and we'll use batches of 16. As you know, we'll be using unet for as our core network, and this unet is actually based on the encoder autoencoder models. We will use one of the encoders called TIM efficient B0. I'll talk more about this later in the sections. Similarly, we'll use imagenet weights. We'll use a pre-trained model and kind of a transfer learning. So we assign this here. Now the next step is just to read the CSV file. Here you just use pandas, read this CSV file and create a data frame. This is just displaying the head, just to give an idea what is there inside. You can see there is a mask and there is an image. So there are 2 columns, and it actually includes the file and associate actually the image and associated mask. This just displaying some of the selected images. You'll see here, and that's very important. When you read a file from CV2, actually by default it reads in the BGR. We need to convert our files to RGB, and that's what we are doing here. So we read the image and then we convert this image from BGR to RGB. Masks are always in the grayscale. We are dividing it by 255 just to normalize them. And then you can see this is what we are displaying. This is our image. This is the ground truth in the data set. This is always a good practice to visualize some of the data sets before we get into more detail. Then here, as it's a standard practice, of course you can always change it to a different thing, but here we are splitting training our training test data set into training and validation. So we are using a training test split function here. We are passing our data frame and we are getting 2 data frames, that is train data frame and validation data frame. We have used test size as 0.2. That means our test set, our total data set will be divided into 80% for training and 20% for validation. For augmentation or data augmentation, we are using this library. You can see the details here, what are the different functions and how it works. We are just going to use simply three of them, and that I'll explain you in the just below. We import this library, it's augmentations, and we defined two methods which will just return the augmentations, are they're also called transformation in more PyTorch language. And what we are doing here is we are composing a number of augmentations, so we just call a compose. We need to do a resize, so we are resizing the image. We are keeping images as square, so that's why you see image size passed twice, and always apply is true, so we are always applying it. Then we are doing a horizontal flip with 50% probability. We are also doing a vertical flip with a 50% possibility, and we have given this flag is check shapes false, so we are not checking for shapes. If you make it true, or if you don't pass this, there are some different data sets in the data set, so it may give error. Similarly, we do for validation data set. We also pass an argument, and we just resize image. Remember, the image size have to be same, but we don't have to do a flipping when it's a validation set. It's absolutely not needed. Although if you do, there is no harm, but you don't need it actually. Then now we go and create a custom data set with a data augmentation. Here we just wrap our functions in a class called person segmentation dataset, and we pass dataset as a parameter which is coming from torch utils data package. We initialize it as usual. We pass a data frame, we pass augmentation, and we just assign these two parameters in our init method. Then length method, this is again a standard method which need to be overwritten for the data set, where we just return the size. This is very important, and this is used to get each image and associated mask in the data set. We again override it, and we pass index because that's what is used for getting those different images and associated masks. So here we just get the row which have path for images and path for the mask. So we just get the image path and mask path from here. We use CV to read the image, and you see the similar operation as we saw in the displaying. We read the image, then we convert from BGR to RGB. We also read the mask and we read in the grayscale because they are grayscale images. This image just because it's a grayscale, it does not have a channel information. But for our processing, we need channel information, so we just expand this image with adding one extra column, and that is axis -1. That means it will be added in the end, and it will become height, width, and channel. Right? For this image, there will be height, width, and 3 as a channel because there are 3 colors in this. So when there is a augmentation defined, we just pass these augmentations here, and we get image and mask after augmentation. Now once we've got this, it is important to put the image in a right order because normally PyTorch tensors expect channel, height, and width, where our images are in height, width, and channel. So that's what we are doing here. We are basically doing a transpose. We're calling numpy transpose here, and you see 2, 0, 1. So that basically means the 2, which is the here, right? The channel information we bring as a first column, and then this is height and this is width. So we just change to this. We also do the same for the mask, and we do it irrespective of augmentation is applied or not. Once we've done this, we convert this numpy image to a PyTorch tensor, and we normalize them by dividing by 255. That's what you see. We call a torch tensor, which takes a numpy image and numpy mask and returns us image and mask tensors. Remember, now we here onward will not use any numpy. We'll use torch tensors for all processing. Then here we just create training and validation set. And basically we pass augmentations. So you see that in the training set we are passing get train IOX. So that means training augmentation functions. In this we pass validation, and then we have training set and validation set. We also check their size. We have 232 records in training set, and we have 58 in the validation set. We just again display here just to make sure that everything is fine. We are using, if you look, we are using the training set index here, and we're just showing those images. Now once we have a data set available, the next step is to create batches for the data loader, which will be very easy to iterate through. Here so far we have created the data set. Now we'll create batches of the data set using the data loader class. Here you saw we use the data set from torch utils data. Here from torch utils data we'll import data loader, and we'll use this to create batches. What we do, simply we'll use the data loader class here. We'll pass our training set and validation set. We'll pass the batch size, which we have defined earlier as 16. Here you'll notice that for training loader we have put the shuffle as a true, so that in every batch there is a shuffling happening in the record set for effective training. For validation we don't need to shuffle it. So here we have just created batches. We have total 15 batches for training data set, and we have 4 for validation data set. And this is just to show you how the tensor will look like. So as you see, there are 16 records per batch. So this is the batch information. Then this is a 3-channel image because it's RGB, and then this is size. This is batch, this is channel, and this is the image size. As you see, this libraries are missing here because I just restarted the runtime. So let me just restart the runtime, run all. So that the libraries are imported. Once we have this, this is a Torch neural network. This NN module library, very important library in Torch. This is PyTorch segmentation models. You might have seen we installed it earlier. You can see details of this right here. So these are the pre-built segmentation models in the PyTorch, which we can use. We don't have to write code from the scratch. You can see there are so many models available. We will be using unet, and there are simply so many. Okay, it's a big number. If you're interested, you can go through it. This also have some interesting losses defined. Normally we use dice loss for this kind of problem. I'll not go into detail in this section. Okay, let me change runtime here. Change to GPU, save. Okay, I have crossed the limit, so it's all right. Okay, we'll just walk through it. So once we have data loader, now we create the model using the pre-existing SMP, that is segmentation model. We'll be using dice loss, which is good for this kind of applications. You can read more details. We define a class called person segmentation model. We pass NN module. Then we initialize it, and as it's a standard practice, we call super with the model name. Then here we define a variable called architecture, and as you see, we're using SMP unet, the networks I showed you. We are using encoder here. If you remember, we initialize the encoder in the beginning. Then we'll use encoder weights as imagenet weights we'll be using. Since we are using an RGB image, it's a 3-channel image, so that's what we are passing here. Classes, here you see one. It's one because it's a binary segmentation. There is only one class. You saw it, it's either 0 or 1, so that's why we are saying it, and we are not doing any activation here. Then we define a forward method and we pass images, and mask is an optional. Why it's optional? Because you also do forward in inference, and then you don't have to actually pass a mask. You just pass the image and get the mask. For training, we need to pass forward. We use logits, and we just get the architecture. This whole thing we pass in the unit. If mask is not defined, if mask is defined, then you process. Otherwise, if it's no mask, you simply pass the image through the network and you get the inference. So now when mask is defined, you calculate the dice loss and use a binary mod here, and you pass logits and mask. Then you also calculate the BC logit slots, and you return these two things, right? So when the mask is passed, you return logits, that is actually prediction and loss. When there is no mask defined, you only return logits. Then you create the model. Actually, this model, it will create the model. You see here error, ignore it. It's coming because there is no GPU available, and I have made this mandatory. So that's what this runtime found no NVIDIA driver on your system. Once you have GPU, it will work fine. Okay, then you move the model to GPU. That's what we have done in this whole thing. Now here we have just a training function, a very standard training function defined. So we pass the data loader, we pass model, and we pass optimizer. Model.train, that means we are saying that this will be a training mod, so that gradients will be calculated. That's one key thing which will happen when we say this. We initialize total loss to 0. We get images and mask from the data loader, and we wrap in the TQDM this data loader just so that we see the progress. Here we just move these two images and mask to the device for processing. Then we initialize optimizer zero gradient. Okay, here we are just calculating the loss. That's what we are doing here. So here we have a prediction and loss. We calculate here. We need to propagate the loss backward because it's a training. Once we propagate, we call optimizer step, which will these two combined basically will make sure that we have this back propagation happening and weights are getting adjusted. Okay, so this will propagate loss and adjust weights. Then we calculate the loss. You see that we call item here just to this is basically your loss will be in a slightly different form. In a tensor form, we just get one item here, and then we return the total loss, which is we return the average loss, which is the total loss divided by the length of the data loader. We have similarly evaluation function. The key difference here, you see that model eval is called here, so there won't be any backward loss propagation or optimization. We have called this method because we don't want gradient to be calculated. We'll save our GPU time. Then inside it, we do the same as a training. We get the images and mask. We push them to the GPU. We get the prediction and the loss, and we return the total loss. You'll notice here that we are not calling a loss backward or optimizer step in this because we don't need it. It's just the evaluation. In the previous method, you saw we are using optimizer. There are many optimizers defined in Torch Optim package. We are using Adam as an optimizer. So we create an optimizer. We pass the model parameters. So basically all our model is passed here. And we pass the learning rate. We can also pass momentum if required here. Now, actually here the actual training is happening. You see that for number of epochs, as we defined in the beginning, we had defined 30. We call the training, we calculate the training loss, we call the validation, we do a validation loss, and we have defined best valid loss as infinity. So each epoch we calculate the validation loss, and if validation loss is better than the previous validation loss, we just save the network here. Okay, so the model is saved. Every time we find a better model than the previous one, we save it here. We assign a best validation loss as a validation loss so that we can continue iterating, and we just print the progress details here. Once we are done with the training, now it's very simple. We just select some image. Just for our purpose, I have given index is equal to 4. You can select any of the images for that matter. You load the model which you just saved in the previous step, and it's available here in the content based model. You can see in the right side when you run this. Then you call the validation set. Once you have done this, you just call the valid set. You take the image and mask with this index. We actually predict the value here. As you can see, model values we are predicting. and we are not passing any mask, so it will just predict. You will see an unsqueezed 0 is called here. Why? PyTorch always have a batch information in it, so when it returns, it will return the PyTorch always requires a batch information, but here we are just passing one image, so it will have channel height and width. However, we need batch, so we are just putting one here for one batch. We also apply sigmoid on it. We have not applied any sigmoid function or softmax in the training. You would have not noticed, so we just apply it here, and here we just convert. If predicted mass is greater than 0.5, we just make it 1. Okay, just to not have too many values, and that's it. Then here we just call our helper function showImage. Here we are passing image, mask, and predicted mask. We'll also see detached CPU squeeze 0. Why this? Normally, when we are doing processing, you saw that we are moving the image and mask to a GPU. So normally it will be residing in GPU, and if you try to display, it won't. So that's the first thing you do. You detach and push to CPU, and then you squeeze it. Why is squeezing? Remember, here we unsqueeze it to create one extra, but when we are displaying, we don't need the batch information. All we need is channel height and width, and that's why it is here. So that's it. Now we have created a method which can segment human body from a given image and display the segment. Thank you so much for watching. Happy learning. And remember, this segmentation can be applied for many different problems. I'll show you in my GitHub. You go to the HumanSegNet. You'll see details here. You'll also see the different other methods which I have not explained here. There are different other methods available for computer vision, like thresholding, clustering, watershed segmentation, active contour models, super pixel model, music multi-scale segmentation, and hybrid approaches. I have not explained that because now predominantly we don't use these. Deep learning methods are very effective now, and where it can be applied. So it can be applied in various fields, including medical image segmentation, like cell segmentation, body part segmentation. It's very effective. In autonomous driving, you segment what is there in your LiDAR, and you can use that. Object segmentation, it is very effective in many industrial processing, like you can identify specific object for pick and place, and so on and so forth. This is also used in painting, like DALL-E and other algorithms you might have seen now. So if you want to replace one image or one object from an image and replace with something else, this is very effective. It's also used in augmented reality. This is not an exhaustive list, but some of the list. All right. Thank you so much. Have a nice day.